Cardinal Turkson, President von Braun, thank you for sponsoring the conference and making it possible, and Vandelay for doing everything. In 2019, there was a celebration at the University of Frankfurt of the Stern-Gerlach experiment. Everyone who knows quantum mechanics knows of that experiment, and if you don't know quantum mechanics, the experiment is incomprehensible. So I will just talk to people who know about it. The reason is that at the celebration for that experiment, I learned many things about Otto Stern, which I had not realized. I don't think many physicists know these things, and I thought they would be interesting and appropriate. So this is a summary of that conference. In fact, there is a summary which has been published in a wonderful book. It's up there on the board, Molecular Beams in Physics and Chemistry, edited by Bretislav Friedrich and Horst Schmidt-Barking. It's open access, so if you dial that book on your computer, it will come up for you so you can see it for yourself, and it's well worth looking at it. It has beautiful personal memoirs by friends and relatives. There's a wonderful biography of Walter Gerlach, who's not that well known, and there is marvelous histories in detail. And what I'm talking about today is largely drawn from that book. The background on Stern, I'm going to start the background in 1912. He was born in 1888, yeah. But in 1912, he had just received his PhD and was starting out on his first job. Now, he had a remarkable career, and he had a remarkable first job. His first job was with Einstein. Einstein had just been appointed professor at ETH in Zurich, and also professor at the German University in Prague. And for some reason, he appointed Stern to be his first assistant. I'm not quite sure why he did that, because Stern was relatively unknown at the time, but it turned out it was a good choice. They got on very well, and a lot of Einstein's sensibilities rubbed off on Stern, as you'll see in how he conducted his career. The career with Einstein ended prematurely with the war, in 1914. At that point, Stern enlisted in the German army. He was appointed to the University of Frankfurt as an assistant professor at the same time, with the understanding is he would start his duties when the war was finished. Einstein actually moved to the University of Berlin, where he had been appointed professor. So their formal associations ended at that point. During the war years, Stern did outside reading. And one of the things he read about was some experiments or demonstrations by the French physicist Desnoyers, who really invented the molecular beam. And Stern became fascinated with the concept of that, he had a free-roaming imagination and started imagining precision measurements in physics that you could do with that technique. And in fact, his lifetime was devoted to exploiting the properties of the molecular beam. Now, if you've never seen a molecular beam, here was Stern's drawing to show you. On the left, there's a little box. That's a stream of material that you would like to see or study. The atoms or molecules would fly out. They would go through a collimator and go to a far wall where they could be imaged or some device to image them. This gave a splendid opportunity to do experiments. You had space for the apparatus, and in particular, what you have space for is a large pump. Vacuum pumps were very crude in those times, and this experiment required good vacuums so that nothing else interfered with the atoms. And much of the progress of the field was just associated with the progress of vacuum pumps. Now, Stern decided for his first experiment that he would measure the speeds of atoms and molecules. This had never been done before. You could look at pressure of a gas, you could look at collective properties, but you couldn't tell how fast the particles in the gas were moving. And he thought this would be an important thing to do. There was a prediction of it, the Boltzmann distribution. He wanted to check for himself whether it was correct, or perhaps some quantum effects were influencing it. Quantum ideas were just being born about that time. So he drew these drawings to explain the principle of the measurement. You have an atomic beam. He started with 2 atomic beams. The little cartoon at the left shows the setup. At the very center was an oven with apertures in each direction, right and left. The beams are tightly collimated and collimated further to make them very, very small. And they hit the walls on each side, but the walls were the walls of a spinning drum. And the spinning drum had slots in it. So the atoms all left in approximately the same time and flew to the wall, and the fast ones would get to the wall right away. The slower ones took some time and the wall would have advanced. So by looking at these patterns, you could measure the velocity speed. Here is some of his data. It's very illustrative of his powers. The lower curve on the right is the Maxwell-Boltzmann distribution, and those little dots are the theoretical values. Most people looking at that would say this is just beautiful agreement. The thesis is proved, but his standards were higher than that. You blow it up, you can see that the little points are not on the curve, they're quite close by. By analyzing these distances, he could get a realistic value for the uncertainty in the disagreement, which was a few percent. He was very disturbed by that. He thought that he should get perfect agreement. So he set to work, and what he found was that there was a mistake really in the apparatus, that a timing wheel, which should have had 400 slots in it, had actually 406 due to a manufacturing error. So he wrote very strong letters to the manufacturer about being more careful. When he compensated for that, he felt the experiment had proved its point. But that just shows his incredible tenacity and his worship of honesty. On the Stern-Gerlach experiment, which was the next one that he undertook and the most difficult one that he did, this was an investigation of quantum theory, which is just being proposed. That wrong way. Yeah. The Bohr atom had been published in 1912, and two theorists independently decided that it led to some absurd consequences. It was called spatial quantization, which meant that if you looked at particles which are moving freely, that you will not find arbitrary results, that their positions would be quantized just because they were in a strong magnetic field. Both Stern and von Lau, who was a colleague that he had met in Zurich, who had actually won the Nobel Prize, became very good friends, and they discussed this in their walks, which were frequent, and they concluded that these ideas were totally nonsense, and that if they were proved correct, they would both eat their hat. They made this as a public bet, so there is no harm in repeating it. But it does show the amount of skepticism about quantum ideas at that time. Only a minority of physicists were concerned with them. Most felt this was just one of those screwball fads which come up. The experiment started about a year and a half after he proposed it. That Stern proposed the experiment in a letter in the fall of 1900. And here is a picture, actually, of the original apparatus from which you can get no information at all, because nothing is apparent there. But the size of it tells you something. The total distance from the source to the detecting plate was about 6 inches, 15 centimeters. It was a very small apparatus, not a very large one. It made use of inhomogeneous fields, varying magnetic fields to control the motion of the atom. And here is their first data when the experiment worked. On the left is a picture of the image of the beam with all the magnets turned off. On the right, the deflecting magnets turned on. The magnets which should induce space quantization turned on. And the important thing about that data on the right is that there are no atoms in the center. No, there is no way to explain that by classical physics. You should find atoms everywhere. This is such a dramatic disclosure that even Stern said he was so surprised he could hardly believe it. Most people who saw it could hardly believe it too. It had a huge impact. I learned about this impact firsthand from I. Robbie. Robbie was a young American postdoc who visited Stern's labs in 1827. And he said at the time, while they were working, that there was a constant stream of visitors, of visiting physicists who wanted to come and look at the apparatus with their own eyes because they found the results so incredible. So 5 years after it had been announced, it was still causing a big stir in the field. The next thing he turned to was the discovery of matter waves. Now, the quantization of the association of wavelength with electrons had been announced by de Broglie several years earlier, and it had been a key idea in the development of quantum mechanics that Einstein was very influenced by that idea. He liked it immediately. He talked to Sommerfeld, and he also talked to Schrödinger. And in fact, Schrödinger picked up on this idea to develop his version of quantum mechanics. So it was a very influential idea, a very appealing, physically natural idea in a sense. But Stern was not satisfied with that proposal because this was individual electrons acting as waves. What about matter as a whole? Would a lump of matter have a de Broglie wave associated with its motion? There was no answer to that question, so Stern set out to find the answer. He found the answer by looking at the wave properties of atoms as a whole. The experiment they did was to diffract a stream of helium atoms from a surface of a crystal, in this case sodium chloride salt, and because the crystal was periodic, it would diffract a wave, but ordinary atoms would just reflect speculatively, but no other way. Anyway, this is an example of the results of that. There's a reflected peak in the middle, and on either side, there are sidebands just where you'd expect the wave to be diffracted. So he proved that bodies themselves, large bodies, also had the de Broglie waves associated with them. He was disappointed. Everyone was so excited about the Stern-Gerlach experiment. No one would talk about this, but he himself felt that this was his major contribution to physics. The next thing he decided to look at was Einstein's prediction that when an atom absorbed light, it would undergo a recoil. Now, that's very well known now. It's the principle of laser cooling, which has probably been involved in 3/4 of the experiments being talked about here today. But it had never been observed. It was the sort of thing that Stern would like to observe. And he did it with a straightforward but crude experiment. On the right side is a thin wire which is coated with silver. So the silver beam would fly out, be collimated, and go to a surface where it would deposit itself. Actually, the source wasn't silver. It was sodium chloride. It was a sodium beam. In the middle, between towards the right, he irradiated the beam with sources from strong sodium lamps, so that the beam would be deflected, and you could measure the deflection. Deflection was very small, but it was observed, and this experiment, it was also done with Robert Otto. Frisch, thank you. Yeah, I should know the name because when Frisch fled from Germany, he fled to Cambridge University, And about 3 decades later, I took a course in quantum physics from him, but he never mentioned this experiment. Anyway, he concluded the experiment. He saw the effect. It was duly recorded. It was small. It didn't make a splash, really. And the people who later developed laser cooling discovered that Klisch did it first, only afterwards. The last experiments I'm going to talk about are the magnetic moments of the proton, deuteron, and neutron that Otto first discovered all of these things.
No, that's fine.
5 minutes. All right. He used deflection methods to find these moments. Very clever ones. He did it with molecular hydrogen and managed to eliminate the effect of the electrons. Magnetization was huge. The first thing they found was the, there he is at that age. Yeah. He found they disagreed with theory, particularly with the neutron, which was expected not to have any magnetism at all, but it had a robust magnetic moment. The magnetic moment of the proton was 4 times as large as it was expected from the Dirac theory. The result of these experiments was that the Dirac theory at that time had to be dismissed. It caused a lot of work for a lot of theorists, which of course a good experimenter wants to accomplish. So these 4 experiments are seminal to our understanding of atomic physics today, of quantum theory today. And that's why I consider them sort of magical. And this was done within a very short time, relatively speaking. And that's why I think that Otto Stern had a magical year. Thank you.